Hello and welcome again to the course graph, theory, application, algorithms and implementation. Today is the lecture, so we'll be covering planar graph. This is the most shortest chapter in the graph course. So what do we mean by a graph is planar? So a graph is planar if it can be drawn in the plane with no crossing edges. So if I can draw a graph without having crossed edges. If I can do that, it means it's a planar. So for example, this graph, it could be drawn like this, and it's a planar. So planar graphs have received a great deal of attention over the years because of a long-standing problem. So they studied a lot the problem of the coloring of a planar graph, and it took like more than 100 years to prove that a planar graph is colorable. So we'll talk about that later in this part. So the planar graphs remain very important today, so because they are applied, they have a lot of applications. Mainly they are crucial in problems such as facility layout, in operation research, and in design of printed circuit boards in computer science. So in our outline here, we will cover some of the planar graph application at the end of this part. So first we will talk about planarity, then we'll move to the planar graph and the coloring of planar graph. So namely, we'll talk about the four colorable conjecture, and then we will talk about duals, graph duals, how we can calculate the graph duals, and how we can apply that to a facility problem application. So as we have said, the planar, it means there's no crossing. So for example, here we have K4. So as you can see, I can draw K4 like this. So K4 is 3 regular, so each vertex has degree 3, so there's 3 edges from that vertex. So I can redraw that graph differently. So I can move one of the vertices to the middle, and our graph is a planar. So as we know that, for example, trees, they are all planar because there is no cycle. So obviously I can draw it without any crossing. And also unicycle graph. So if a graph contains just one cycle, they are a planar. So a graph might be planar even though it looks a non-planar. For example, K4, it looks like it's non-planar, but however it is planar. So as you can see, planarity is a potential. If you have the potential that it could be drawn without any crossing. So if there's some way to draw a graph without edge crossing, the graph is a planar. So if a graph is a non-planar, so obviously there are some edges that needs to be crossed. So the number of edge crossed, it's called the crossing number of the graph. So obviously we should have the fewest number of crossing number or crossed edge. So a plane graph is a graph that is drawn in the plane with no crossing edge, obviously. So if there is no crossing edge. So we have examples. For example, K5 is not planar. We will see it in a while. So the crossing of K5 is equal to 1. So I can draw K5 with just one crossing. It means two edges, just one crossing. It means just two edges that cross. So K5 can be drawn with one pair of edge intersecting. So we have also an intuition here. So for example, if a graph A is non-planar and A is a subgraph of B, so obviously B is also a non-planar. So if A is subgraph of B, and if A is not planar, so obviously B is non-planar. So we'll use this in order to verify that a graph is non-planar. So we already know that K5 is non-planar. So obviously for Kn, and for n is greater or equal to 5, any Kn is non-planar because of this intuition. So we can say that K1 till K4, they are planar. So this is for just a complete graphs. For example, let's say for K1n, so K1n is the star. So there's one here, and there's an edge with n vertices. So obviously since K1n is a star is a 3, so it's a planar. This is K2n. K2n is also a planar. K3n, we can show that is non-planar. So K3n is non-planar for n is greater or equal to 3. And the crossing number for K33 is equal to 1. So if I want to draw K33, let me erase everything here. So this is K2 n, this is K33. So as you can see, there's a lot of crossing. However, I can redraw K33 with just one crossing. So I can, for example, place those in the middle, and I will place one here, and one here. So I have this first one, the second one, and then I have this here, and I have just one crossing, which is here. So I have just one crossing whenever I'm considering K33. So obviously KMN is non-planar, and where M and N are each at least equal to 3. So M and is greater or equal to 3. So it's very nice to play with all these. So in the practice, you will have some exercises where you need to work around some graphs so that they are planar. So we have an example here. So they are telling us redraw the following graph as a plane graph. So we know that it's planar, so we need to redraw this graph. So as you can see, you need to find a way to remove all this crossing. So for example, so I have the animation here. So we have, for example, FB. So I can, for example, move it to the outside of the graph. The same for FC. You know, we still have AD and EB. So okay, I can also drag it like this. So let's see what we can do. So for example, I have those all crossings. So I can remove AD. I like it like this. BE also like this. So now I have no crossing. So also we have some theorem here that it says that if I have an edge that is curved, I can redraw the graph using straight lines. So, and this is the planar graph corresponding to that graph. So I'm just moving C here and doing all the modification in order to have straight edges, not curved edges. So, and this is the same graph here, but it's a planar graph. So let's move on to Euler, because Euler, you know, he's the father of the graph theory. So obviously he worked on planar graphs. So the great Euler noticed that a plane graph divides the plane into regions. So this is a planar graph. So as you can see, there are regions. There are region A, region B, region C, and the outside region, which is D. So one face, the outer face is of unbound extent. So those are the faces, and the outer face is D because there is no bound for that. So there's a formula for Euler which says that if we have a graph which is connected, it contains n vertices, q edges, and n f faces. We have the formula n minus q plus f is equal to 2. So let's do it quickly here. The number of vertices is 1, 2, 3, 4, 5. So n equal to 5. The number of edges is 1, 2, 3, 4, 5, 6, 7. And the number of faces, there are 4 faces. So n is equal to 5 minus 7 plus 4. So I have 5 plus 4, 9. 9 minus 2 is equal to 2. So the formula is verified. So this is Euler formula. And this is true whenever we have the graph is connected. When the graph is not connected, so it has multiple connected components, the formula would be like this: n minus q plus f is equal to k plus 1, where k is the number of connected components. So in our case, k is equal to 1, so we will have the same formula. However, if we have multiple connected components, so this is the formula of Euler. So we have also some relations and theorems about the number of edges in a planar graph. So if a graph is planar, obviously with vertices n is greater than equal to 3, and it has q edges, then we know that q, number of edges, is less than or equal to 3n minus 6. So it follows that directly that if the graph is planar, delta, the minimum degree of the graph, is less than or equal to 5. So those are theorems and corollaries, so we will not prove them, we'll just directly use them. So as another theorem and corollary, so we know that we have already covered that in one of the practices. So we have the girth of the graph, so it's the length of the shortest cycle. So whenever I have, for example, a cycle, a triangle, or any cycle, any C, so the girth is the length of the shortest cycle. So again, if the graph is planar, if it has n vertices, q edges, and it has a finite girth g, then the number of edges is less than or equal to the girth multiple n minus 2 over the girth minus 2. So it's again a formula that tells us a lower bound about the number of edges. So if, again, as a corollary, if the graph is planar and it has n vertices and q edges and there is no triangle, so in the case where there is no triangle, so there is no g here, so the number of vertices is less than or equal, the number of edges is less than or equal to 2n minus 4. So those are some theorems about the number of edges in a planar graph. Let's move to another definition, which is the subdivision of a graph. So let's, given a graph G, so a subdivision of a graph is a graph that can be obtained by inserting any number of vertices of degree 2. So for example, I have here the graph G. So H is a subdivision of G. Why? Because I have inserted 1, 2, 3 vertices of degree 2, as if I'm just placing some dots. So I'm adding vertices, but at the end, at the same, as if it's the same graphs, but we'll call it a subdivision. So even J is a subdivision of G. So it means this is equivalent to replacing certain edges by passes. So this edge I'm replacing by a path, so I'm just adding vertices. So we have a theorem that it's due to Kuratowski. So a graph is planar if and only if, so you should pay attention because we'll be using a lot this. So a graph planar if and only if it contains no subdivision of K5 or K33. So we already know that K5 and K33, they are non-planar. So if we have a graph and we can make a subdivision of that graph that it contains K5 or K33, so we are sure that the original graph is non-planar. So for this we have an example. So we need to prove that the Peterson graph is non-planar. So we have a lot of ways to do that. So the first way, so as we can, so let's use some of these formulas, about the number of edges, if it's correct or no. So we know that the number of edges here, Q, is equal to 15, so you can count it, and the number of vertices is equal to 10. So we can test the inequality. So we know that the number of edges is less than, let's go back, it's equal to 3 multiple n minus 6. So it's 3 multiple 10, which is the number of vertices, minus 6. So 15 is less than 24. So for now, the formula is correct. So the inequality is correct. So it doesn't tell us that the graph is planar or non-planar. It tells us that it could be a planar, since the theorem, it tells us if the graph is planar, then we have this inequality. But if we had it in the reverse order, so if we have the wrong inequality, we could have proved that the graph is non-planar. However, this formula didn't help us to check whether this graph is non-planar. So we need to check another tool. So another tool is to use the subdivision. So either I can try to find K5 as a subdivision of Peterson graph, or I can find K33 as a subdivision of of the Peterson graph. So as you can see here, K5, it means each vertex, it has 4 degree of 4, since K5 is 4 regular. And as you can see here, each vertex here is of degree 3. So obviously I cannot find, so I cannot use K5 in order to say that it's a subdivision of Peterson graph. So I need to pick K33 and try to find a subdivision of the Peterson graph that contains K33. So for that, we'll label the Peterson graph as follows, and we need to make it a way it looks like K33. So I need to, as I have said here, I need to add some vertices in order to make it look like K33. So let's see. So a subgraph of the Peterson graph is subdivision of K33. So we will redraw it to clarify that. So I will just remove that. So I will draw A, B, C, D. So I have here A, B, and I will link it to B, C, D as it is. I have I, I'm trying to do the remaining one. So I have redrawn the graph, the Peterson graph, a subdivision of the Peterson graph as a subdivision of K33, as you can see. So I have omitted here this vertex, so HG, so I have omitted it because it will not help us, and either GF, it will not help us even if it's inside the graph. So as you can see, I have redrawn, so it's potentiality. Obviously, you will not be able to do that by your own. So I have redrawn the Peterson graph as a K33, and since K33 is a non-planar, and we will just apply Kuratowski's theorem, so we are sure that our graph, our Peterson graph, is not a planar. So this is the way that we can prove that a graph is non-planar. So either we can find a subdivision of K5 or a subdivision of K33. So this was for the planarity. Let's move to the coloring of planar graph. So the question arises here is that how many few colors are needed to color a planar graph. So why this question is very important? It's very important to map makers. So for example, if you are doing maps, you are coloring maps, so a map featuring countries with shared boundaries, it's easier to read if adjacent countries are colored differently. So in the internet you can find a lot of colored maps. This is easy to see and easy to understand, and this is why we are very interested in coloring a graph, especially planar graph. So there is a strong connection between maps and planar graph. A map consists of set of contiguous countries. So for example, this is, for example, a map. Let's say that I have a country here, another here, and we have here. So I have 1 region, 2, 3, 4, and 5 region. So how can we transform this map into a planar graph? So we can represent each region by a vertex and then link those adjacent vertices. So I have the A, B, C, D, E, and I will do the linking. So I have this graph, so the graph where the dashed edges. So the transformation from a map to the corresponding graph is related to the dual of the planar graph. So this is what we call dual, and we were covering in the third part. So the transformation converts the problem from one of coloring region on a map to one of coloring of the vertices of a plane graph. So this is the output. So as for the coloring, so it's very it was like the researchers in graph theory, they have spent more than 100 years in order to prove that, and it took them like more than 700 pages in order, and they use the computer very much in order to prove that every planar graph is 4 colorable. So they took them a lot of time. However, the formal proof says that every planar graph is 5 colorable. So we have a formal proof for 5 colorable, and we have an computer assisted proof for 4 colorable. So whenever you see a planar graph, you can color this graph by at most 4 colors and no more than 4 colors. So in the coloring practice, the first exercise, you had a planar graph. So I didn't say it's planar. And obviously, now you are able to solve that directly, and you can directly say it's 4 colors, that you don't need more because it's a planar. So this was for the coloring part. So let's move to the last part, which is the graph duals and the planar graph application, which is about the facility location. So in order to talk about the application, we need to cover first what we call the dual of a graph. So a planar graph, as you can see, it divides the plane into regions. So this is a graph. It have faces, as we have already covered. So those are the faces. We have here 4 faces. So the degree of the face is the number of edges incident with it. So for example, I have F1. So as you can see, there's 1, 2, 3. So the degree of F1 is 3, since it's adjacent, is incident with 3 edges. The degree of F2 is equal 1, 2, 3, 4. So remember, those are 2 edges. So the degree of F2 equal 4, of F3 equal to 4. As for F5 is 1, 2, 3, 4, 5. So the degree of F4 is equal to 5. So those are the faces, and each face, it has its degree. So what we call a dual. So given a graph, this is the graph with faces F1, F2, F3, Fk. So a graph G with faces F1, till fk. So the dual graph, which we call it G star, is as follows. So the vertices, the set of vertices of G stars, they are the faces. So we'll redraw it now in a while. And the edge set is obtained by placing an edge between vertices of the faces for every edge shared by those faces. So let us repeat it quickly. So the dual is a graph, so the vertices is the faces. So here I have 4 faces, so I have f1, f2, f3, f4. The edges is whenever there's an edge in common between those faces, I will place an edge here. So f1, f2, they share one edge, so I will add one edge between f1, f2. Between f2 and f3 there are 2 edges, so there should be 2 edges. Okay, I have done this one first, so let me just redraw the graph. So between f2 and f3 there are 2 edges. So as you can see, this is a multi-graph since there are multiple edges. Between f3 and f4 also there is 2 edges, those 2 edges. So f3 and f4 there is 2 edges. Between f4 and f2, as you can see, so there is 1 edge between f4 and f2. So this is the outside. There's 1 edge, this is here. Between f4 and f1 there is 2 edges. Between f4 and f1 there is 2 edges. So this is the dual graph of the graph G. So the vertices are the faces, and whenever between any 2 faces we count the number of shared edges and we place the edge in the dual graph. So as you can see, we have here some remarks that the dual graph is a multi-graph. So why is a multi-graph? Because you have multiple edges between any 2 vertices. So since the dual graph is a graph, so we have the same theorems as we have covered in the first chapters. So the sum of faces degrees, so the sum of the degrees is equal to the twice number of edges. Also, so if the graph is of order n, so the dual graph has n faces. This is very easy. So graph order n of order n. So if it has n vertices, so the dual graph, it has n faces because the vertices will correspond to faces. So again, for any planar graph, we have the dual of the dual is isomorphic to the original graph. So let's continue and talk about how we can represent the dual of graph whenever we have bridges. So for example here y, it's a vertex that doesn't share anything with f1 and f2. So we'll see what we will do. So the following graph, for example, it has bridge xy. So in the dual graph, the vertex corresponding to the outer face f3 will require an edge not shared with any other vertex. So this is a very special case. So we'll see it in a while. So the edge in the dual graph with the vertex f3 twice is called a loop. So we should add a loop in order to have this. So the resulting graph will be called pseudograph. So I will draw it for you now and see what we will do. So I have 3 faces. So in the dual graph we have 3 vertices which correspond to the faces. f1 and f2, they share just 1 edge. f2 and f3, so they share 2 edges. So f2 and f3, they share 2 edges. Between f1 and f3 also they share 2 edges. However, I still have f3. So f3, for example, this edge is shared between f3 and f3. So as you can see, for example, f3, there's 1 edge shared with f3. So I will add a loop in f3. So whenever we have a bridge, we add a loop. So it's already drawn. So let me erase everything in order to see that. So those are 2 edges. Those are 2 edges. This is 1 edge and this is a 1 loop. So we have an exercise here. So we need to draw, or given the planar graph, redraw its dual. So I will do it directly on the graph. So I have here a face, so it's a vertex. I have here a face, it's a vertex, and here also. And let's say the outer is here. So we know that between this one and this one there's one edge, because this is the shared one. And so obviously we have all these, and again between this face and this face we have one. Between this face and this face there's one here, and obviously there is one here. So this is the dual graph of this graph. As for this, so you know that we have here a loop. So I have here a face, I have here a face, and let's draw the face here. So obviously I have here just one edge, because this is the one edge between those two faces. Between this face and this face, so I have two, because I have two edges. So let's draw it, one like here and one like this. So the same for this one. So I have one edge and a second edge. And since we know that I have one bridge here, so it needs a cycle, a loop. So this is my dual graph for this graph. Let's move to the last one. So again, I have here faces, so each one is an edge, and I have an outer one which is an edge. So between each of these there's just one. So this is easy. And between the outer face and each face there's just one edge. So this is the dual graph. So I have them maybe on the screen. So let me erase everything. Okay, so let me not laser but done. So we have the solution on the graph. So let's do another exercise. So given the plane graph G, draw its dual, then list the number of vertices, edges and faces of both graph and its dual. So we have here 5 faces, they are already given. So just as you can see, so we have here a bridge and we have here a bridge. So obviously you will have 2 loops in the dual graph. So we have here f1, f2, f3, f4, f5, so the same as here. So let's do it together. So between f1 and f2 there's just one edge. Between so I don't know where's the animation. Between f1 and f5, so there's 2 edges. Between f2 and f5, again there's 2 edges. Between f3, so f3 it has a loop. Between f3 and f4 there is 2 edges. Between f3 and f5, so let's count that. We have 1, 2, 3. So this is why we have 3 edges. Between f4 and f5 we have 2. Between f5, so we have f5 and f5, we have 2 loops. So why we have 2 loops? Because we have one which is here and one at vertex f5. So one at vertex f3 and f5, because we have this outer edge which is a bridge, and the second one is for this one too. So the graph has 12 vertices, 15 edges and 5 faces. So obviously here we have 5 vertices, 15 edges and 12 faces. So this is for the duality of the graph. So since we have covered the dual graphs, let's move to the application, which is the facility layout. So for example, when designing the layout of a facility such as libraries, hospitals, shopping malls or department store, we sometimes wish to make certain regions adjacent to certain others. So for example, near the restaurants we like to have the restrooms. For example, near the theater we have the dining section. For example, we like to have the closest store next to each others, the kids region next to each other. So we have some preferences. So let's take an example here. So suppose that we have 8 departments or 8 stores, so located they are labeled, sorry, between A to H. So and they are planned for within a new department store, and the desired adjacencies are as described in the table. So we like to have A next to BFH and B next to ACF and so on. So first we need to draw the graph with vertices corresponding to the department and each edge corresponding to an adjacency. So this is easy to see. So I have the A to H vertices, and then I'm linking A, B to F, so I'm doing the graph. So if the graph is planar, so it's easy to satisfy all the requirements. However, if the graph is non-planar, so it means that it depends on the crossing number. So if there are some crossing, it means those adjacency I will not be able to satisfy, because there will be something in between those values. So we need to check if this graph is planar, and if it's planar, we need to redraw it in the sense that there's no crossing. So how can we do that? First, so you need to follow these, because in the practice you will have a similar exercise. So whenever you need to find that, so first you need to find an Hamiltonian cycle. So if the graph is Hamiltonian, so the graph here is Hamiltonian. So I will remind you that a Hamiltonian means I can visit all the edges once. So I can start from a vertex and return to that vertex and visit every edge at most one. So the graph here is Hamiltonian, and I can find a cycle. So let's suppose that we have the edges within the Hamiltonian cycle C. So we can pick any Hamiltonian cycle. I'm not giving it to you here. However, in the exercise, I'm giving it to you, and you should stick with the Hamiltonian cycle. So we have this cycle. So we have the edges, which is inside where there's crossing. So we have labeled each edge that contributes to the crossing. So for example, AB, it's not labeled since it's not crossed with any other vertex, any other edge. So for example, AF is crossed with HC, is crossed with GC, with HE. So there's 3 crossings. So this is why the 1, it will be connected to 5, 4, 3. Why? It's the crossing. So I have AF, it crossed with HC, which is equal to 3. So I have an edge between 1 and 3. I have also an edge between 1 and 5 and 1 and 4. So this graph is called the edge cross. So each internal edge joining non-adjacent vertices on the cycle C becomes a vertex in the new graph. So we have this is a new graph, and 2 vertices are adjacent if the corresponding edge cross one another. So the graph, this is the graph. So we can say that the graph is planar if and only if the crossing graph, the chromatic number, the edge chromatic number of this graph is equal to 2. So if the edge chromatic number of this graph is equal to 2, it means that the graph is a planar. However, so as you can see here, this graph is not two colorable. So it's not, we cannot color it with using 2 edges. Why? Because it contains a triangle. So there's a lot of triangles in this graph. So for example, this is a triangle. So we have this is a triangle. So we cannot color the crossing graph using 2 colors. I'm talking about the edge chromatic number. So if I want to color the edges, so I cannot color the edges using just 2 colors. So for example, if I color here red, if I color here blue, so I cannot color this neither red or blue. So I need another color. So whenever we have a cycle, we cannot do that. So this graph, this crossing graph is not too colorable in terms of edges. So this graph is not planar. However, what we can do is that I try to color these edges. So what can we do? For example, I can color let's say one, I don't know. So let's see what we can do. So we can color so it's not planar. So what we can do is that I can, after doing the coloring of the crossing edges, the crossing this one, so I will keep it for you as an exercise, I can take out one of the colors. So for example, those edges, I will take them out of the graph. So I will move them to the out, and the other colors, I will keep them inside the graph. So obviously those will not have a crossing. However, here, as you can see, I have just one crossing. So I have reduced the number of crossing, which was a lot, to just one crossing. So now I can redraw. So this is just a facility layout, just a visualization of what we can do. This is not the only solution. So we can redraw the graph, and we display one possible floor plan. So as you can see, the adjacency between C and G here is not verified. So they are far, they are not adjacent. So because I need to break one of these, so either C and G they are not adjacent, or H and E shouldn't be adjacent. So H and E they are adjacent, however C and G they are not adjacent. So so the layout, as you can see, is a starting point for the designer whenever you need to design something, for example later on to do the cabling of the wiring for the internet and the Wi-Fi and stuff like that. So a weighted graph could be used to help model additional desired conditions such as the relative size. So there are more general facility layouts studied where we specify distance, for example, between departments. So we want to maximize the sum of all the distances in the final layout, while at the same time trying to satisfy as many of the distance constraints as possible. So this is a very broad subject, so we'll not cover it much more. So this was for this part. So it's very short, it's very interesting, it's very useful also. So if you have any questions, do not hesitate to use the forum or write to me. And again, thanks for watching.